Yeah. All right, so some logistics first. I'm going to upload the. No, sorry, let's backtrack. I have had some trouble uploading the last lecture onto Google because it wasn't downloading from Zoom properly, but it seems to have this morning. So I will upload the last lecture onto Google. As well as onto the YouTube channel a little later today. Your exercise sheet 1 should be ready for upload today. There's enough material to give you something to work with. I usually give a week to work through the problems. They're not difficult problems. This first tutorial is more or less a revision of some complex analysis as well as some stuff in gamma function. So it shouldn't take you too long. Ostensibly, I'll set it in a week, but if you need extra time, it's not going to be right. Your tutors, of course, are listed, and we've appointed a new tutor as well. Of course, Claudia. Nitin and Paul will be in contact with you via Google or email. And set up the tutorials for the. Okay. Any questions? Yes.
I know one more of this. Something that last week. Reading for.
Yeah.
So it was showing that the path is for the circle we have from A to.
Hold on, you mean quadrant?
I mean constant.
Yeah.
Sorry. And of e to the t to the z minus 1 t equals 0. You said in the notes at z equals 0, the time equals 0. In your notes, I found something that said it's equals some analytic function. I assume that's using the Gaussian Grosart theorem.
Grosart, yeah.
Yes, but in that theorem it says that it has to be a simple closed contour, and obviously it's not closed without its function.
Well, there are. So, okay. So you can. So Gaussian Grosart works for any simple closed contour or deformation theorem. So when I said, we start off at minus infinity and head out to the origin, go around and go back, you're really meant to think of the limit as epsilon goes to 0. That this function goes to parallel line goes to 0. So really you have a closed contour. But actually, even before that, you have a closed contour. This is a deformed closed contour because it heads out to minus infinity. Right? You start with minus infinity, come around the origin, you go back out to minus infinity. Minus infinity is a point. Right? If you want to think about this more geometrically, then don't think about the complex plane. That's infinity, right? Think about the complex plane mapped to the sphere. So you start off at the north pole, at the south pole, right? Come out to the origin, and you go back to the south pole. Really the same point. So it's a closed contour. Just one point is stretched way out. Okay. Right. Good. Any other questions? about logistics, so far, blah, blah. All right. So today I want to cover three things. I want to pick up where we left off last time talking about Lorentzian amplitude. And I said that you've got this remarkable behavior that was super simple, and we were trying to understand why these resonances play on straight lines. It's hopefully something that happen often complicated resonances. So now we'll introduce the Lorentzian amplitude, and I'll show you what Lorentzian's guess was with this amplitude, and what's related to a combination of gamma functions that we call it or a beta function. Let's explore a little bit of the properties of the beta function, and depending on how much time we have, I'm going to start the next section, which is elliptic functions, and I want to introduce the idea of elliptic functions through studying simple pendulum. Okay. So we're going to be talking about the pendulum, which you've seen since first year already. And typically, when you think about the pendulum, you think about simple harmonic motion. We're going to go beyond simple harmonic motion this section. Okay. That's the point. All right. So I want to consider two mesons scattering. I don't really care that they're mesons. I just want to consider two particles that are scattering. And I want to try and outline how we think about this in particle physics. So consider the elastic scattering of two particles. In particle physics, this is a complicated system. If you've done scattering theory, not even in quantum field theory, but in quantum mechanics, then you know that the math can get quite complicated. But there's a nice diagrammatic mnemonic, if you want, was discovered by Feynman, which, for those of you that are doing my topics in string theory course, that's where we're building towards this mnemonic on how to treat problems like this. But I can tell you about this mnemonic without worrying about the details of what it actually means, right? Essentially, Feynman taught us that we should think about this system in the following way. I have some incoming particle, some charged particle, and I have some other incoming particle, some other charged particle, and represent charged particles in these diagrams by lines with arrows, so directed lines. Okay? The directed lines correspond to charge data. So we're going to have neutral particles. There are no lines without arrows. Something happens when these guys scatter off each other. We represent some big box. And charged particle goes out. And the charged particle goes out. So I have two incoming particles and I have two outgoing particles in this file. So what I do is I find a way to label these particles. So let's label them 1, 2, 3, and 4. And each of these particles carries some momentum. Right? So we'll assume we're working in 4 dimensions here. We represent the momentum to some 4 vector. So this is some Lorentz vector, which I'm going to call P mu. This will be, for example, corresponding to particle 2. This will be P mu corresponding to particle 1. The corresponding momentum P mu 3. Okay. So far I've done nothing particularly deep. All I've done is label this diagram. I'm telling you that this diagram is a mnemonic, don't take it seriously. There's a bunch of math underlying this mnemonic, which again we'll unpack in other course, but not taking the course, it's not really necessary to understand what's going on. The point here is that from these momenta, I can actually form 3 variables. The first one I'll label S, and S will be minus P mu 1 plus E mu 2 whole squared. And this is the center of mass squared, the center of mass energy squared in appropriate units. Center of mass energy squared. There are two other variables that I can form. They're denoted by T. And T is minus P mu 1 minus P mu 4 squared. And then finally, there's U defined to be minus of P mu 1 minus P mu 3. These variables are not arbitrary variables. They're chosen because they code the kinematics of the scattering problem. These are what's called Mandelstam variables. Anybody heard of Mandelstam variable? Yeah? So you know that Stanley Mandelstam was a South African physicist who graduated at Wits. The Mandelstam Institute at Wits is named after him. Okay, so these are the Mandelstam variables, and they code the kinematics of the scattering problem. Okay. They're not independent variables because they satisfy one constraint. That is that S plus T plus U sum up to sum from, say, I equals 1 to 4 and I squared. So they satisfy one constraint. Three variables, one constraint. There's two independent variables in this problem. Okay. Usually, those independent variables are taken to be S and T. And they allow us to resolve this diagram in two ways. It's called the S-channel stacking and T-channel stacking. So you can resolve the diagram to two possible diagrams. One is called the S-channel diagram. Which has my incoming particles, 1 and 2, interacting through some intermediate particle, which I don't really care about, but I'm going to denote by these dashed lines, and outgoing. This is the S channel. The other one is the T channel. It's the same diagram. So incoming particle 1, incoming particle 2, outgoing particle 3. This is called T channel. Okay. So that's just some background to this problem. So Veneziano asked himself the following questions. Can I think of an amplitude, scattering amplitude for this meson process? This meson scattering process that has the following properties. So can we find amplitude that has the following two properties. One, it has poles wherever there are resonances in either the S or T channels. Right, so again, I take these two particles, scatter them off each other, and I watch what comes up. Right, what comes up, some excited states, these are the resonances. I'm looking for an amplitude, roughly speaking, the square root of the probability distribution of this process, such that wherever there's a pole in the amplitude, there's a resonance. So we're trying to replicate that linear relationship that we found that was found with Reggie scattering. That has poles where there are resonances in either S or T channels. And two, it doesn't have double poles. In other words, these poles don't occur with squares in the denominator, right? So there's circle poles. So does not have double poles. The reason you don't want double poles is because they spoil the unitarity structure of the theory. And so I want a well-constructed, well-defined, not problematic theory. Again, I want an amplitude that has poles where there's resonances, in either the S or the T channels, or and doesn't have double poles. Okay? So Veneziano realized that there was this function. Okay, so Veneziano made the following guess, recognizing that the gamma function has poles whenever its argument is a negative integer. Remember we found or 0 or negative integer, not positive. So 0, -1, -2, -3, all the way up to infinity. The gamma function has poles, right? Simple poles. So Veneziano guessed that the scattering amplitude A depends on the Mandelstam variables S and T might look something like gamma of alpha of S. Remember, alpha was this function that characterized, sorry, minus alpha of S, function that characterized the Reggie scattering. Gamma of minus alpha of T divided by gamma of minus alpha of S minus alpha. And this guess would satisfy the two constraints that we started off with. That's poles at each of the resonances in the S and T channel scattering. This was a phenomenological we observed fact. And it doesn't have double poles. So the theory that we're working with remains unitary. Now remember, this was prior to the days of QCD. And this was back when we just had all of this data coming out of the particle physics experiments, trying to explain the structure of this data. And it turns out that Veneziano's guess, Veneziano amplitude, the pole structure of this amplitude is exactly the same as the energy angular momentum relation for a string, whose string tension goes like 1 over the slope, the Reggie linear relation, 1 over alpha prime. So it's a rotating string with tension that goes like 1 over alpha prime. And this was really the birth of string theory. Back in the day, they were calling it dual resonance theory because it's trying to explain these resonances. And we're going to frame these resonance problems as not as particle scattering, but as a rotating string with some string. So this is the same, by way of comment. So this is the Veneziano amplitude. And this was the same as the energy angular momentum relation for a rotating string with tension say T that goes like 1 over alpha prime. The alpha prime is of course the reduced slope. So this being a course in methods in mathematical physics, that's as much as I wanted to say about physics and motivators. I'm really interested in this particular combination of gamma functions, right? Gamma of something and gamma of something else divided by gamma of that something plus something else. That's the structure. Okay. This leads to the idea of the Euler beta function. Which is this particular combination of gamma functions. Gamma of P, gamma of Q, divided by gamma of P plus Q. It's like a beta, it's actually a big data beta. And you can see that the Veneziano scattering amplitude was really just a beta function. Which means that all of the properties that were known about the beta function back in the day suddenly were open to exploration by these particle physicists trying to understand these resonances. Because the scattering amplitude satisfied these properties that we wanted to phenomenologically explain the resonance structure was just the Euler beta function. Okay. Okay, good. So let's explore then some of the properties of this Euler beta function. The first thing is I would like to get an integral representation because I think one of my goals in this first couple of lectures is to convince you that getting integral representations for functions is complicated. Is a really powerful way of working with these functions. Okay. And I don't actually need to know an expression that's a closed form expression for this function in order to deduce many of its properties. Okay. So let's explore some of the properties by starting off with I'm going to start by assuming that the real part of P and the real part of Q are both positive. So the first thing to note is that we already have integral representations for the gamma function. So maybe we can use those integral representations of the gamma function to kind of figure out what the corresponding integral representation is. It's not going to be entirely trivial because I have sticks in the denominator. And really what I want is one integral representing all of this stuff. But I do know that numerator is certainly easily enough to integral, if I assume the real part of P and Q are positive, I can immediately write down integral representations for the product, and integral representation for the product of these two. This is just the integral from 0 to infinity of s to the 2p minus 1 e to the minus s squared yes integral from 0 to infinity t to the 2q minus 1 e to the minus t squared. I've taken the standard integral representation, the defining integral representation for the gamma function, and I'm going to change the variable from s to s squared to t squared, note down the appropriate integral measures, and that's where each of these factors of 2 came from. Okay. So I look at this, and I notice that there are these quadratic terms with the exponential, and that tells me that find the monopoles. Okay, so I'm integrating, these are iterated integrals, 2 one-dimensional integrals, and I'm integrating from 0 to infinity, so positive s axis and positive t axis. So when I combine these two into a double integral, I expect to integrate positive s, positive t. That tells me that I'm looking at the first quadrant. Are you with me? So if we change variables, this thing is equal to, again, I'm setting s equal to r cos theta, t equal to r sin theta. Yes, that combination of gamma functions, ds dt becomes r dr d theta. So this is just 4 times the integral from 0 to infinity of r to the 2 times p plus q minus 1 e to the minus r squared dr times the integral from 0 to pi by 2, because again we're integrating the first quadrant only, of cos to the 2p minus 1 theta sine 2q minus 1 theta to theta. We've seen this integral in the last lecture when we were trying to derive the conversion formula for the integral representation. One factor of 2 times this guy is nothing but the gamma function itself. It's the gamma of q. So the thing here is half of gamma e plus q. And then I have this integral of sines and cosines, which I have to think about. But if you don't have to think about it, because this is just 2 times gamma of p plus q times the integral from 0 to pi by 2. This stuff. And I recognize then that gamma of p, gamma of q is 2 gamma of p plus q times this. So if I divide 2 by this gamma of p plus q, then I find my first integral representation of the beta function. Beta of p q is just 2 times the integral from 0 to pi by 2 cos 2p minus 1 beta sine q minus 1. That gives us our first integral representation for the beta. There are already some remarkable observations that we can make. One in particular is the following. The beta function, the way we've defined it, should be clear that it's symmetric in P and Q. Right? So if I exchange P and Q in the definition of beta function, I get exactly the same thing, because who cares whether I'm doing gamma of P, gamma of Q, or gamma of Q, gamma of P. And this, if the denominator is P plus Q, is the same as P plus P. So what I'm trying to say here is that this thing here is obviously the same as gamma of Q, sorry, beta of QP. Right. So the left-hand side of this integral is symmetric in P and Q. That's an obvious fact in the definition of beta function. It's not obvious from this integral representation. However, because these two things are the same, this integral must also be symmetric in P. Okay. So, these are the kinds of things that you learn about integral representations. This is a horribly complicated trigonometric integral where it's absolutely not obvious that if I exchange the P and the Q, the sine and the cosine, it's the same integral, but it is. Okay. So let's make a comment of that. So notice that from definition of beta Q, the integral must be symmetric. So my point here is that if just knowing that somebody just threw this integral at you, okay, then given that this integral is equal to the beta function, you know that it must be symmetric in its parameters. Even though this is the was the easiest integral representation to get to, it's not the one that's most commonly used when it comes to integral. But we use this integral representation to deduce some more integral representations that are more commonly encountered. In the literature. So I want to derive two of them in particular. Derive let's stop right now to the following. So I'll go back to this integral representation, and instead of considering beta of P and Q, which is like this, I'm going to consider beta of P plus 1, Q plus 1. Well, if I replace P with P plus 1, Q with Q plus 1 in that integral, and I get the integral from 0 to pi by 2 of cos to the 2p plus 1 beta sine to 2p plus 1 beta. It's an entirely trivial statement so far. And now I want to change variables. So I'm going to define t to be cos squared of beta. And if I define t to be cos squared of beta, then it's clear that sine squared is related to cos squared because sine squared is just 1 minus t. Okay. And then this is cos 2p plus 1. There's a 2p there, and there's an additional cos factor. But if I define t to be cos squared, then the integral measure dt is 2 cos theta sine theta. So one factor of cos gets absorbed into the integral measure, one factor of sine gets absorbed into the integral measure, and I can get all of those things into dt. The integral goes from 0 when cos is, when theta is pi by 2, cos is 1. And so this integral will run from 0 to 1.
I wanted to make sure this is not the same t as the one.
No, I'm just going to use t. It doesn't matter. It's an integral, it's a dummy variable in the integral. Okay. But the point is that when I do this, I can absorb the factor of 2, one factor of cosine, one factor of sine, and a d theta. And the integral will go from 0 to 1. T to the p times 1 minus t sine to the q dt. And then of course I can go back to p and q by just replacing in here. Okay, and that gives me a second integral representation for the beta function. Stable this. Yeah. Set t equal to x squared. And we'll get another representation. It's commonly used, which is that this is 2 times the integral from 0 to 1 of x to the 2p plus 1. 1 minus x squared to q. Yeah. And you should check this. Similarly, if we set t to be u over 1 plus u, we will find that beta of p plus 1 from 1 gives us an integral from 0 to infinity of u to the p over 1 plus u to p plus 2. That's integral representation. So each of these integral representations, and I would like you to check this as well. Each of these integral representations is useful for a particular purpose. Okay, when you're studying scattering amplitudes, you're interested in angular variations as these particles come out of this SMD channel. And so it makes sense then to express the beta function in terms of polar vector. When you're studying conformal field theory, either condensed matter physics or string theory, for example, then this integral representation is the one that's most convenient. So which integral representation you use depends really on the problem that you're trying to study in the first place. Okay. And again, there are many different there are many different integral representations, and there are many properties of beta function that we can derive from these integral representations. So here's a quick calculation for you to do. Again, this derives from this relation derives from doing two things. One, we've been working with P and Q being positive, being complex numbers with positive real numbers. Right? In the same way that we've been doing so far, I can extend this definition to the whole complex plane by analytic continuation. Right? So I can just replace the P and the Q with Z, for example. So as a quick calculation, using integral representation, I would like you to prove the so-called duplication formula. Says that gamma of Z plus 1 times gamma of Z plus half is the square root of pi over 2 to 2Z gamma of 2Z plus 1. And you can see immediately from the structure of this duplication formula that the beta function is going to be involved. Z plus 1 and Z plus half. Z plus, I can relate this Z plus 1 to Z plus a half using the recursion relation for the gamma function. In the case of Z plus a half and Z plus a half, and Z plus a half plus Z plus a half. So this relation can be proved using the beta function, and I'm going to give it as an exercise for you to prove it. And there are again a number of different results that can be proved in a similar way. Okay, any questions? No? So now I want to move on. Then we've covered the Venetian amplitude, showed you how to make the beta function, and we've used these relations to explore some properties of the beta function, like interpretation. So now I want to move on to the next section, which is another set of special functions called elliptic functions. Are you guys familiar with elliptic functions? Anyone that's not familiar with elliptic functions? I know you don't need to know it intimately, you just need to know what the definition is, so some intuitive idea for what it is. Yeah? Okay. So the elliptic functions are generalizations of trigonometric. I'll explain the generalization this time. So trigonometric functions are periodic. If you didn't know anything else about trigonometric functions, then you know that they're periodic. They're periodic and they have a single argument, and they're periodic in that argument. So there's some direction, x or y if you want, in which the trigonometric function is periodic. So we say that trigonometric functions are periodic in a single direction. Okay. So sines, and cosines, tans, cots, etc. These have the following properties. One, they are analytic functions on the entire complex plane. two, they are periodic in one direction. So what I mean by this in particular is I can think of, instead of sine of x, I can think of sine of z, cos of z. Z is a complex variable. There are two directions involved, the real part of z and the imaginary part of z, and everything else is a linear combination of those two directions. But sines and cosines are periodic in one of those directions. You pick one, say x direction, and sine is periodic in x. I'll find it repeating after some period, 2 pi instance. Right? So these are examples of functions that are analytic on a complex plane and periodic in one direction. The question, one question you could ask is, and I'll come back to the geometric interpretation of these analytic functions in a little bit. I want to make an analytic question to start. Can we think of, are there functions that are analytic and periodic in two directions? Okay. So something that's periodic in both the x direction and the y direction, both the real part of z and the imaginary direction. Okay. These are the two properties that I want, and I'll first make an argument that will allow me to deduce what these functions do, if you want. Functions map domains into ranges. I would like to understand what domain, what range. And I can make that argument by just expanding on this question. So, and the properties that I want the functions. So suppose some function exists. That is to say, I have a function and it's going to be analytic and it's going to be periodic in two directions. Okay, a real direction and a complex direction. Well, the function can't be analytic everywhere, because if it's analytic everywhere, and sorry, there's a third, so 1.1, they're bounded. Okay. So if I have an analytic function, if the function is analytic anywhere, then it's got to be a constant. Because the theorem of analysis that tells you you have a bounded analytic function. Then it's going to be a constant. So my functions have to have poles somewhere. Got to be singularities somewhere. Okay. And there are at least because I'm expecting, so I'm building these things to be periodic, then the poles have to be periodic. I expect them to repeat every so often. And because I'm building them to be doubly periodic in two directions, then these poles have to be periodic in both directions as well. So what I'm doing is I'm taking the complex plane And I'm saying that our function has to have poles, periodic poles, in two directions. The real direction as well as the imaginary direction. In other words, I'm taking the complex plane and I'm dividing out the lattice in this complex plane, the lattice of poles. Okay. So this here, C modeled out by lattice geometrically is a two torus. In other words, we are looking for functions that map the two torus T2 into the complex plane with infinity included. In other words, the Riemann sphere. Such functions that map the two torus into the Riemann sphere are called elliptic functions. That's all they are. These are called elliptic functions. And these elliptic functions play an important role in everything from geometry to mechanics to number theory. In fact, Andrew Wiles' proof of Fermat's last theorem can employ the theory of elliptic functions and elliptic curves. What were crucial to his proof. Proving Fermat's last theorem, he didn't really prove Fermat's last theorem, he proved something which, if it was true, would imply Fermat's last theorem. This was the Shimura-Taniyama conjecture. So what Wiles did was use the theory of elliptic curves, elliptic functions on plane, to prove the Shimura-Taniyama conjecture, and in doing so, by extension, proves Fermat's last theorem. So these functions play an important role in a vast majority, in a variety of different mathematics and physics topics. There are forces that exist that treat these topics from an analytic perspective, from a mathematical perspective. I really want to give you a flavor of what these functions are and how they behave. Right? They're generalizations of the trigonometric functions. So they satisfy a lot of the similar kind of properties as trigonometric functions do. So, you know, when you learn sine and cosine trig functions in school, you learn that they satisfy things like sine squared plus cos squared is 1, equivalent things with tans and cots and cosecants. These guys satisfy similar kind of problems. But you know, the fact that sine squared plus cos squared is 1 and x squared plus y squared is r squared is why we say that trigonometric functions are defined on a unit circle. Okay, so trigonometric functions are defined on a unit circle. These guys are elliptic functions for good reason. You deform that circle into an ellipse, and they're defined on an ellipse, which means that you should get something like x squared over so whatever the equivalent of sine is for an elliptic function, whatever the equivalent of cosine for an elliptic function. with some additional coefficients summing one. We're going to derive these relations, but I want to do it in an intuitive way. So I don't want to bog you down with the analysis and actually some of the geometry as well. So we're going to study these functions. I'm going to define these functions from a physical problem. The physical problem is a pendulum. Okay, so I want to consider a simple plane pendulum. And draw a picture of what that looks like. I'm going to anchor the pendulum at the origin, and it's going to have size L. So here's the pendulum. Some size, mass attached to the end of the pendulum. I don't really care what that mass is. Ignore that mass. It's going to have length L, and place the pendulum. Make some angle theta with the vertical axis. And this theta is going to be a function of time. Right? Okay. So what I want to do today is just set up the problem for you. So we're not going to go too much more into it. We're going to set up the problem and set up the equation of motion. And then next time on Wednesday, we'll solve those equations of motion. I'll show you where it is. So here's the deal. I have this pendulum, I have gravity acting on the pendulum, on the mass. Gravity acts downwards. Right. Acceleration of g. And I have this theta of t here. This is theta. So normally, what you would do is you would assume that the oscillations are small, so theta of t doesn't vary too much, and the pendulum stays oscillating about the vertical like this. We're not going to be so restricted in our consideration. And so I'm interested in what happens, for example, when I give this guy enough energy and it goes around the circle. So theta of t can really get as large as 2 pi. In fact, I'm giving enough energy that it can just keep going. And I would like to understand how theta of t behaves. So my goal here is to write down some evolution for the angle of theta. Yeah.
Is it attached to a string or
It's attached to a rod of length L. It's a stiff rod, yeah. Okay. So the kinetic energy of the pendulum K is a half m v squared. And the v here is the linear velocity, it's the tangential velocity at any point. This tangential velocity is half m L times d theta by dt. So I'm going to do d dot squared. And so all in all, this is a half m L squared theta dot squared. So if you've studied the pendulum before, you've seen this expression from the potential energy of the pendulum is such that it contributes to the kinetic energy, its maximum at some point, minimum at some point. Right? So down, so in our system, the maximum that the kinetic energy, I can take this guy and release it down here, the maximum that the kinetic energy is going to have is at 0, the y-axis, in the y direction. Right? So I'm going to use, and at that point, the potential energy is 0. Okay. So energy sloshes back and forth between the potential and the kinetic. So I'm going to zero the potential energy at the horizontal position, because all the energy is kinetic at that point. And with that, the potential energy is minus mgl times cosine. So note is that 0 of potential is at the horizontal position. So I put this together in the Lagrangian of the pendulum. The Lagrangian L is a function of the angular theta as well as the angular velocity dot, and it's just the kinetic energy minus the potential energy. So that's a half m L squared theta dot squared plus m g L plus theta. From the Lagrangian, I can derive a set of dynamical equations that govern the mass. Those dynamical equations are governed by the Euler-Lagrange equations. Euler-Lagrange equations are basically that dl by d theta minus d dt of dl by d dot equals 0. So if I differentiate, I will find that the equations of motion by the following set of equations of motion for theta. That is theta double dot, second derivative of d plus theta with respect to time is minus g over L sine theta. These are the equations of motion. Okay, so just as a calculation, we should check this. Okay, so at this point, the standard approach would be, I would say, okay, if the angular variation in theta is small, then I can approximate sine theta by theta. Theta is small, sine theta is approximately theta. In which case I've got theta double dot is minus something times theta. So I'm looking for a function whose second derivative is that function itself, except the minus. That will allow me to deduce that theta to be a sinusoidally or cosinusoidally varying function with time. Okay, so that's a harmonic approximation. So we assume that theta is small, which means that sine theta is approximately theta, and our equation of motion is theta double dot is approximately minus g over L theta. This implies that theta of t is some constant cos t plus some constant sine. Okay. The question we would like to ask here is how do we go beyond harmonic approximation? Okay. So that's what I would like to do next time, and I will introduce the idea of elliptic functions as solutions of the differential equation that we program. Yes. Any questions from online?
None, Prof. Thank you so much for the session.
Sorry?
No, I don't have any questions for now, but thank you for the session.
Okay, you're welcome.
Yes, I've been following and the YouTube videos, they're also assisting.
Great, fantastic.
All right, thank you.
Okay.
Nothing on the side as well.
Okay, great. Thanks, guys.
The last